I have no papers because there seems to be no one at the office. Nobody has made any copies for me. So I have to talk from the top of my head. No problem, I can do that. So I have some questions about the previous paper. Okay.
What to do if I...
So which limits? 8.
No.
8.
No, number 19.
Okay, just tell me the numbers very quickly. 8. You said 18.
19.
19. Oh, okay, there are 2 18s.
Yeah.
So obviously both of them. So both of them.
27.
27. All right. Okay, let's go through these quickly, and then I want to move on to the 2 special limits. By the way, I am reminding you that I will not be here on Thursday the 13th, so you are free from me, at least for that one afternoon. And then on the 17th and 18th, nothing happens. We sleep, or have fun, or party, or whatever. Take part in the fun in the city. There are going to be a lot of events in the city, and in the evenings you will see the light effects, the lights festival. But I will see you on Thursday the 20th. Yes, Thursday the 20th. That day will be devoted purely to practice. It has to be, because we have our limit test on Monday the 24th. Monday the 24th will be the limit test. Only limits, nothing else. Because functions are covered by this homework. And so on Saturday before that, the 22nd, I will come here for those who want to come for some extra practice, for questions about limits perhaps. Also some, well, I know that some people want to retake vectors, but please, you have to let me know in advance so that I can prepare the papers for you for that Saturday after, well, in 2 weeks, in a week, 1.5 week, right? So I'll devote that afternoon to practice, questions, test retakes if you need them, and so on and so on. But for the test retakes, I really need to know in advance so that I can prepare the papers. You know that when I get angry about cheating, I start preparing individual papers for everybody. So I need to know how many papers to prepare. Okay, so try to figure out, those of you who do want to retake the vector test next Saturday, and try to let me know in advance, perhaps during the holidays, not in the last moment, not on the 20th, because that gives me almost no time to do this, but well, perhaps during the holidays or during this weekend, or well, any time you remember, but remember soon enough. Okay, so that I can prepare the papers for you. And the limit test is the 24th of November, Monday. Before that, on Saturday, if anyone needs some more explanations, some more help with limits, will be welcome. But then you have to choose whether you want to retake the vector test or ask me limit questions. Actually, limit questions are good for Thursday, because for Thursday I actually have revision exercises for limits, preparation for test, including more difficult limits perhaps. So all kinds of limits.
Yeah.
All right. Number 8. Limit when x tends to 1. Limit when x tends to 1. X minus 1 x squared plus 2x minus 3. It shouldn't be difficult. So of course this is if we try to use 1 for x, we get 0 over 0, that's an uncertainty. And if we have the uncertainty of the kind 0 divided by 0, we try to factorize and divide out that 0 factor. In this case, well, the problem obviously is that you have forgotten factorization. You have forgotten how to factorize quadratic trinomials. All right. So some of you might have been taught at school to look at these and just to figure out how to do this. Another method is if it's difficult to find the roots, if it's difficult to find those factors, then you might think of it in terms of solving a quadratic equation by the formula if you want. So x minus the first root, x minus the second root. So basically, this is a formula for factorizing any quadratic trinomial. If you cannot do it on the spot, just by looking at that trinomial, then you might find the roots by the formula, use the quadratic formula, the discriminant, find the roots, and you can factorize it like this. Actually, of course, it's easier for you if you can factorize a quadratic trinomial immediately just by looking at it. You can think a little bit and figure out the numbers. But anyway, so we see that we can cancel out that evil factor, which creates zeros in the denominator and the numerator. So we have now 1 over x plus 3, which means 1 divided by 1 plus 3, it's 1/4. It's not difficult at all. So if it seems difficult to someone, then it means you have forgotten how to factorize. I'm not even considering the option that you never knew how to factorize. Number 18.
No. I meant number 19.
You meant number 19, all right. You meant number 19. Yes, I know. Okay. That's number 19, which pretends to be number 18. You're welcome to correct the number. All right. So we have limit of 4 to the power x divided plus 3 divided by 2 to the power x plus 1 as x tends to infinity, obviously the positive infinity. All right. Any suggestions? Any ideas?
What?
Because at this point, if we simply put infinity instead of x, 4 to the power infinity, of course it's infinity, 2 to the power infinity plus 1 is of course infinity. So it's the uncertainty infinity divided by infinity. We have to figure out what to do about this kind of limits. So yesterday we did not discuss limits with exponential functions.
So you divide everything by 2 to the power x.
Yes,
Yeah.
let's divide everything by 2 to the power x. Let's divide everything by 2 to the power x. So we have now, this is easier, 2 to the power x plus 1 divided by 2 to the power x is simply 2. That's easier. Plus 3 divided by 2 to the power x, no problem. Law of logarithms.
What?
Wow, logarithms. I don't see a single logarithm here. Better not. Better not. But if you want to divide 4 to the power x divided by 2 to the power x, what happens?
2 squared.
Remember that we can to 4 divide the bases and use the same exponent. Remember how we deal with division or multiplication of powers that have the same exponent but different bases. And what do we do when we have different exponents on the same base? Remember, we have the formula a to the power m times a to the power n is a to the power what? M plus n. M plus n. So actually the algebraic operation taking place in the exponent is, let's say, one level less than the one we need for the powers themselves. If I want to divide a to the power m by a to the power n, then that means I have to subtract, even if the exponent becomes negative. It simply means 1 divided by a to whatever power. And then there were another 2 rules for division and multiplication. For the situation when we have the same exponent but different bases. For example, a to the power m times b to the power m. just a times b to the power m. And if I have a to the power m divided by b to the power m, it's the same. I take the quotient a over b and take it to the power m. So you see, if you have a common base, the common base remains. We only change the exponents. If we have different bases but the same common exponent, then we keep the common exponent. We only work with the base. So in this case, because I have 4 to the power x divided by 2 to the power x, it's actually 4 divided by 2 and then taken to the power x. When you did exponential equations at school, you did this sometimes. So what we have here is 2 to the power x after division. And now what this means is, this tends to 0, this is simply 2, but 2 to the power x. If x tends to positive infinity, then we have infinity. 2 to the power x is infinity. Remember the graph, and many of you had to graph this function 2 to the power x. So if x tends to positive infinity, then the power of 2 to the power x will also tend to positive infinity. If x tends to negative infinity, then 2 to the power x tends to, obviously, 0, right? But in that case, so let's consider this. If x tends to infinity, if x tends to positive infinity, then this tends to infinity, this tends to 0, this tends to infinity. Infinity plus 0. If x tends to the negative infinity, then this 2 to the power minus something tends to 0. This tends to 0, but 3 divided by 0 tends to infinity. We still have 0 plus infinity in the denominator. So in this case, I'm simply explaining why I did not put plus or minus in front of infinity, because it doesn't really matter in this case. In this case, it doesn't really matter. In this case, this limit is, okay, infinity, of course, because this tends to infinity and we cannot change that fact. We cannot change anything up there. So it might be the other way around. If x tends to the negative infinity, then this would tend to 0 and this would tend to infinity. But the final result is the same. The final result would be the same. So this limit is infinity. In other words, we can say that there's no finite limit, or a limit does not exist, or we could say that the limit is infinity. If x tends to infinity, the limit is infinity. Nothing really important limit-wise. Okay. So we can see that we need to remember the exponent laws or the properties of powers. That's something that's important, but that's school stuff. Sorry, if you have forgotten, look it up, print it out from the internet.
How about the 21st?
Okay, 21st.
Yes.
All right. 21st. Aha! Limit 2 to the power minus x over 2 to the power x when x tends to which infinity? In this case, negative infinity. Okay. This will be infinity too. Why? Because I can change this. I can either move this down and make it 2 to the power x, or I can make this up to get rid of the fraction of the quotient and make this 2 to the power minus x. Whichever. All right, so I'll move it down. Because if the exponent is negative, that would mean that I have to move this down. So 2 to the power x, it's this one, and this move down also becomes 2 to the power x when x tends to negative infinity. Which means now we have 1 over 4 to the power x when x tends to negative infinity. Now let's think. If x tends to negative infinity, 4, the base, is greater than 1. So this is again this kind of function, this shape of exponential function. Let's remember the shape of the exponential function. When x tends to minus infinity, this tends to 0. So actually this becomes 1 divided by 0. Well, not exactly, but the result is infinity. The result is infinity. Or I could have moved this up and I could make this 4 to the power minus x. If x tends to minus infinity, then minus x tends to positive infinity, right? So we have 4 to the power infinity, which is not really a number, but I put it in the quotes so that you don't take it for a number, it's simply to explain what's going on, what we are looking at. So it would still be infinity. It will still be infinity.
Just one question: if the limit, if the x, well, if it was the positive infinity.
If it's the positive infinity, then we would have 1 divided by infinity. It would be 0.
Okay.
Then it would be 0. So you have to be very careful about which infinity, positive or negative. And by the way, if I have the base of the exponential function less than 1, for example, 2/3 to the power x, remember that that function, that graph looks like this. It's decreasing. The shape is basically the same, but if the base is less than 1, then the exponential function is decreasing. If the base is greater than 1, then the exponential function is increasing. So you first of all, you have to be careful about which infinity, and secondly, you also have to be careful about the base. Is it greater than 1 or less than 1? Two things to think about. But basically, these all work approximately the same way, more or less. All right, so 27. Oh, nice. 27 is just wonderful. There. X tends to 9. Oh, okay. 3 minus square root of x divided by 4 minus square root of 2x minus 2. Alright. Now, if I take x equal to 9, I get 0 divided by 0. Here I have 16 then under the square root, so it will be 4 minus 4, still a 0. So this is first of all uncertainty, 0 divided by 0.
Scare.
And this means that, remember yesterday, we have to multiply by the connected expressions by the corresponding sums. by the let's call them conjugates.
Yeah.
So I'm rewriting this limit, x tends to 9. I'm rewriting this limit, 3 minus square root of x, 4 minus square root of 2x minus 2. Now, to get rid of this square root, so first of all, the strategy is, let's get rid of those square roots that create zeros, because zeros are bad for us. So to get rid of those square roots that create zeros, this creates zeros because it's subtracted, 3 minus 3. So let's multiply it by the conjugate sum. And of course, so that things do not change, I have to multiply the denominator by the same sum. And now I can do it gradually, or I can do it at once, and I'll do it at once. So to get rid of this expression again, I don't like it. I have to multiply the numerator and the denominator by the conjugate sum of this one. So by 4 plus square root of 2x minus 2, 4 plus square root of 2x minus 2. And now we have to be careful. We will not multiply everything. We will multiply the two connected pairs. So we will multiply these only and leave this as it is for now. And from the denominator we will multiply these. connected expressions, and we will leave the 3 plus square root of x as it is. So never open the brackets unless you really, really need it. It's better to wait, and then if you see that, yes, I really need to open those brackets, then I will. But unless you really, really need to open brackets, don't open any extra unnecessary brackets. Better leave the product as it is. And so, what do we have here? X tends to 9. 3 minus square root of x, 3 plus square root of x. That's 9 minus x. And this is, well, we will leave it intact. We will just leave it as it is. In the bottom, below the line, in the denominator, we see 2 more conjugate expressions, so we'll multiply those. 16 minus 2x minus 2 without the square root. I'm using an extra pair of brackets so that we don't get confused with the signs. And times this, 3 plus square root of x, which has no pair. So now we have limit as x tends to 9, so 9 minus x, 4 plus square root 2x minus 2. And there we have 16 minus 2 is 18, minus 2x times 3 plus square root of x. Now what? Compare these two. Now these are the expressions, these are the factors actually that produce the zeros that we don't like. We would need to simplify this part. We would need to cancel out these, divide something out. So if you just notice that this is 2 times 9 minus x, this part. So, alright, let's cancel them out. And so now we don't have to worry about anything at all, because now we only have a sum, we don't have a difference. We have a sum. We will not get zeros here anymore. So we can simply put 9 instead of x. So I have 4 plus square root of 18 minus 2 divided by, so this is cancelled out, obviously, 2 this times 3 plus square root of 9. This is easy to find. So 4 plus root of 16, 4 plus 4 is 8. And here we have 3 plus 3, 6 times 2, 12. So it's 2/3. That's the limit. Yes, it looks a bit complicated if you have to squeeze it on a small page. If your handwriting is such that you tend to squeeze the lines together and so on. But if you have a lot of space, then it becomes easy. I have a lot of space here on the board, so it's very simple for me. Yes?
So for example, if indentation use this kind of motion, and if reversible, then I can solve this question through derivative. But I solve this question through derivative, like taking the 3x to the root of x.
Okay, you want to use the L'Hopital's rule. Now we are in a bit of a spot, so that you want to jump ahead. Obviously, you know your derivatives, you know your calculus, because L'Hopital's rule actually comes after the derivatives. But to get to the derivatives, we need the limits. So it's actually L'Hopital's rule is a very special one, which we can get after we learn the derivatives, and actually it depends on how we prove it, how we prove that. Basically, well, as long as you know the name of the rule, as long as you can make a note of what you are doing there, so that when I read the text I don't see what's going on there, then at least make a note there, make a note to me what you are doing there, that you are doing the derivatives, or you are actually applying the L'Hopital's rule or something like that. I don't think I would like to use L'Hopital's rule for the square roots, because the derivative of the square root is unpleasant enough as it is. Oh yes, most people, those who don't remember derivatives at all, those who have forgotten them. Those who haven't studied them properly will not know the rule. So it's a bit of a problem again, because it's annoying enough to get test papers in which people clearly have copied something from some clever book or for something or someone, and it's clearly too much for their understanding. They have copied mechanically something. And if I ask to explain why did you do this, where did you get the rule, well, you'll probably not be able to explain. So what I would like to see is you people understanding that mathematics. Of course, you don't have to know all the formulas by heart, but if you ignore a simple method I show you and choose a complicated one from whatever handbook, whatever manual, whatever website, it doesn't make sense. Sorry. I prefer to explain and to show things, let's say, in the simplest understandable way, because there are people who don't understand mathematics so easily. So I have to choose the simplest method of explanation so that everybody understands. My apologies to those for whom this is too simple. I can, of course, always invent some terrible limits. Any more questions from this?
Yeah.
What?
14s, they are the infinities, yeah? It's a bit
Okay, this is all right. Number 14. If we look at this, we have x squared over x plus 3 minus x. And this is the last one, because let's keep this then for the 22nd. If there are people who need simple limits explained, then we better leave it for that extra lecture, so that we don't actually delay the necessary material. First of all, we can say that if we try to solve this, we have another kind of uncertainty, which is infinity minus infinity. The difference of two infinities might again be anything at all. Who's to say that these two are the same infinities? So we don't really know. So what we do is, of course, let's take everything on the same line. X plus 3, so that would be times x plus 3, it would be x squared minus 3x. And so it becomes minus 3x over x plus 3. And this is easy to find. This is minus 3. This limit is minus 3, because if we have linear expressions both in the denominator and the numerator, we can simply divide x, that infinity, we can divide it out. So we can divide out x, divide out infinity. We have then minus 3 divided by x1 plus 3 over x. And obviously, if x tends to infinity, then this tends to 0. So we have the limit minus 3. So when you have a simple difference or a sum, then obviously it would be better to bring everything on the common denominator, on the common line. It's much easier to deal with a single fraction than with the two expressions separately and then trying to figure out the difference separately. That would be too unpleasant. Although, yes, it is possible to do it a little bit otherwise, a little bit differently. But in this case, I think this is the most rational thing, because, for example, L'Hopital's rule works if you have a quotient of two functions, which tend to infinity or to 0. So for 0 over 0 or infinity over infinity. So those two types of uncertainties. To solve this by L'Hopital's rule, we would still need to simplify this on the common denominator. Okay. Now the two special limits. Let's see. Perhaps I only have time for one. Sine, yes. We'll do the sine limit first. Okay. So we have this limit when x tends to 0 of the quotient sine x over x. Quite often we encounter trigonometric limits of trigonometric expressions, trigonometric functions, and up to this point we have only been dealing with algebraic functions only, which means powers, polynomials, radicals, and that's all, and well, perhaps some exponential functions. But we have not been dealing with trigonometric functions at all. On the other hand, quite often we see that there are some trigonometric limits. So this limit actually equals, so put 0 in there, 0, sine of 0 is 0, x is 0, so this limit is actually 0 over 0. That's an uncertainty. So this is an uncertainty. How do we solve this?
Maybe we can write sine of x like cosine.
Cosine.
Minus cosine under the square root.
What would that help? 1 minus cosine squared. If x tends to 0, cosine tends to 1, and 1 minus 1, it would still be 0. It wouldn't help. In this case, it wouldn't help. We could change sine into cosine, square root of 1 minus cosine squared. But the problem is it wouldn't help. Because if x tends to 0, so we know that sine of 0 is 0, but cosine of 0 is 1. So 1 minus 1, still 0. So that's not something that might help. But the thing is, so let's have perhaps a look at the first quadrant of the trigonometric circle. All right, the trigonometric circle. Remember, if x is there in this situation, in these functions and calculus, absolutely. When we deal with functions, trigonometric functions and calculus, remember that the x is always taken in radians, never in degrees. X is always in radians. So, do you remember what a radian is?
Pi.
No, 1 radian is not pi. 1 radian is
okay.
a definite. What kind? How do we define a radian? Of course, yes, it's 57, whatever. But how do we define a radian? What is a radian? What kind of angle is a radian?
So when two vectors are the same.
Is that kind of shape?
That kind of arc. Okay. All right. So actually, a radian is an angle for which the length of arc is equal to the radius.
Yeah, that's what I want to say.
Okay, so the length of arc is equal to the radius. That then this angle is 1 radian.
What is shape called in English?
Arc. This is arc.
Okay.
This is arc of a circle. Arc of a circle. Compare to the term arc tangent, arc sine, from the sine to the arc, right? And of course, this is a sector. This is a sector. The whole shape, the slice of the pie, the pizza slice. That's sector. But we are dealing with the length of the arc and the radius. So if the length of the arc is equal to the radius, in this case, if it's 1, then we are talking about radians. So then that's radian. In other words, if I have an angle x radians, then it means that the corresponding arc would be x units long. That's important for this limit. That's extremely important for this limit. In other words, if I have angle, okay, I'll put it higher up so it's more obvious. Of course, we are thinking about very, very small angle values. But, okay, so if I have this angle x and the radius is 1, then x radians means that the length of this arc, is x. The length of this arc is x. If we could stretch it straight and measure, it would be x. And we are talking about x radians as the measure of the angle. So we have to understand is that this would be x. Alright, now the sine value. Now let's consider the sine value. I will draw a perpendicular here. So let's suppose this is the point whatever, B, and this will be A. So I draw a perpendicular. Obviously, what is the sine value for the angle x? Can we see the sine value?
On the way.
The PA is actually sine of x. Remember that we read the sine values of the vertical axis. The vertical axis is the sine axis. If we have the trigonometric circle or the unit circle, radius is 1 unit, and we look at the point from the horizontal positive half axis, if we look at an angle and we look at this point obtained by this angle, then we read the sine value of the vertical axis. So this would be sine x at this point. This is obviously the cosine value. OA is the cosine value, but we are not interested in cosines at the moment. Obviously, the sine value is greater than the sine value is actually less than x. The arc is longer than the half of the chord. Right? So the full arc would be longer than the full chord, and the halves, obviously the same applies. So sine x, which is PA, I can write. Okay, I'll write it differently. I will write L. The arc length is greater than PA, obviously. Now I want the other boundary. I will draw a vertical line through this point. A vertical line through this point. Anyone knows what this line is? It's the tangent line.
Yeah.
It's the tangent line. If you continue this radius, OP, if you continue this radius, at this point, you can read off the tangent of the angle. At this point, so this is actually the tangent line. So if you can read off sine on this line and cosine on this line, then here, using the same scale, 0, 1, 2, and so on, you can read off the tangent on this line. I do believe you did have this at school.
Yeah.
Yeah. So I would say this is B, and this is obviously C. I'm putting some numbers there. Obviously, well, it's not so obvious, and this is the one thing I'm going to skip in my proof or in my explanation. PC, it's very obvious it's greater than BA, but it's less than BC, and this is the part I'm going to skip. So you have to look at this. It's somehow, interestingly enough, it's greater than this chord, but it's less than BC. It's less than BC. So it's less. Okay, so just skip the trouble and leave this alone. And so what I have here is the length of the arc is x. The length of PA is actually sine of x, and the length of BC is actually tangent of x. For those who do not believe me, or for those who do not understand why this is the tangent of x, okay, let's leave this until the next Thursday or Saturday when you can ask, where you can ask me more explicitly. All right. So now what we are going to do is take the reciprocals. We'll turn this upside down. Now, we'll turn this upside down. So we'll have 1 over x, 1 over sine, and 1 over tangent, like this. What about the inequality? It changes the direction. Changes the direction this way. Now let me think. So let me think. Yep. Now I had to divide everything by the sine value. All right, let's multiply everything by sine. Let's multiply everything by sine now, times sine x. So we have 1 sine over x, and we have 1 divided by tangent times sine, or cotangent times sine is what? It's cosine. It's cosine. Because this is cotangent, it's cosine divided by sine, and if you multiply by sine, it's cosine. And now, if x tends to 0, what happens? If x tends to 0, then cosine tends to 1. And because we see when x tends to 0, the cosine of x tends to 1. As x tends to 0, this ratio is definitely less than 1, and it's greater than something that also tends to 1. And there is a theorem, or perhaps you can understand it intuitively, it's called the squeeze theorem. If I have 3 functions, or 3 expressions, sandwich, squeeze, depends. Actually, I was taught it as the theorem of 2 policemen. You know, if 2 policemen catch a criminal, one side, the other side, and the 2 policemen go to the same place, jail, then the criminal is forced to go there as well. The same thing, sandwich theorem, squeeze theorem, because actually what we have is sine x over x can be nothing else but 1, as x tends to 0. So this limit simply equals 1. Of course, the problem is that we have many other trigonometric expressions and many other trigonometric limits. It's not always that we say, oh, it's 1, it's 1, it's 1. It would be extremely boring. Problems?
Can I prove this theorem?
Which theorem? Squeeze?
Yeah.
So the squeeze theorem would take the epsilon definition. You wouldn't like it.
The proof.
The proof.
Only for proof.
Perhaps on Saturday when we have time, because we have to work on the limits actually.
Because such equation on our test, we have to write everything.
No. The thing is, this is only the beginning. Wait, we are not halfway through. This is just the beginning. So can I erase that part?
Yeah.
It's simply an explanation how we come to this kind of limit. Simply an explanation. Okay. 3 people understood, everybody else say.
Everybody else says, oh, crap. It became just a lot harder.
Okay, so we have something like this. But please notice it only happens when x tends to 0, only for very, very small angles. Now, if we look at the graph of sine x and x, remember that the sine x looks like this, the sine function, the graph of the sine function. And the function y equals x looks like this, y equals x, y equals sine x. The fact that this limit is 1 means not only that those 2 functions have the same value when x is 0, because it's 0 over 0, then basically it's an uncertainty. But the limit means actually that the behavior of these 2 functions as x gets very small is very, very similar. They not only have the same value, which means they intersect at that point, but they also are very, very close to each other as we approach 0. They are very, very close to each other. And now I'm skipping ahead again. The same obviously applies if the sine function is so close to the y equals x. Then the arc sine function, which is symmetrical to the sine, the graph is symmetrical to the sine graph, is also very close to y equals x. The inverse function, because the inverse function, remember, the graph of the inverse function is a reflection of this graph in the same line y equals x. So if this graph is very close to the, let's call the mirror, the line of reflection, then the mirror image is also, the symmetrical graph is also very, very close, the same kind. So we have actually another limit, arc sine of x to x is also 1 as x tends to 0. We could prove the arc sine thing differently, but I'm only showing you the illustration so that you understand why this happens. Now, if we think about the tangent function, if we talk about the tangent function and the arc tangent function, we'll look at those separately. The problem is, you will actually never, almost never, get this. You will get something like, for example, the limit when x tends to 0 of sine of 3x divided by 5x. Do you think it's 1? No, it's not. Because what we have to notice, yes, some people know, what we have to notice is these two variables in this special limit are exactly the same. In that limit, they are not the same.
1/5 is not.
No, it's not 1/5. So the thing is, for that limit to work, I need to have sine t over t. It has to be the same variable, exactly the same. I have 3x in the sine, 5x below the line. Can I make 5 here? Not so easily. Can I make a 3 here? Yes, I can. I can multiply by 3, and of course I have to multiply the numerator by 3 as well. So in other words, I simply put that factor that I would like to see there, and of course I have to put it both in the denominator and the numerator so that the fraction, the quotient itself doesn't change its value. But now I can see that here I have 3x, here I have sine 3x. In other words, I have this kind of limit. So this quotient tends to 1, and what's left over is 3/5. So I can actually write, I can take this 3 outside, I can take 5 outside because they are not necessary for this limit. And what remains is sine of 3x divided by 3x. So now sine t over t as t tends to 0. Now this is 1. It doesn't matter that we have 3 here and 3 here. What matters is that we have exactly the same expression t. So this limit equals 1. This limit equals 1. And so the final answer for this is 3/5. Just like that. Okay. Another example. So this was the first actual example. The first, okay. Another one, let's suppose we have the limit of tangent x over x as x tends to 0. Okay, tangent is sine divided by cosine. Okay, rewrite ln as x tends to 0, sine x cosine x. I simply rewrite tangent as the quotient of sine and cosine, and now I see that this limit would be 1. What about cosine? When x tends to 0, cosine of 0, remember I wrote it on the board, cosine of 0 is 1. So if x tends to 0, then this, the cosine, also tends to 1. So we see that this limit is 1 also. So the same thing. So there's another limit for our collection of trigonometric limits. tangent x to x also tends to 1. Well, obviously I could sketch the tangent graph. I could sketch the tangent graph there. And obviously then the arctangent graph behaves again in the same way there. So if the tangent, the ratio, the quotient of tangent x to x is 1, then obviously the limit of the quotient of the arctangent function, the inverse function to x, also tends to 1. The short explanation is because of the symmetry of graphs. They behave in the same way when close to 0. The longer way would involve more inverse functions. Tangent x to x is 1. So that's the second special example, which is important. These four limits are set in stone, unchangeable. Yes.
Leaving arc sine of 1 or of x?
That's x. Sorry, my handwriting. Should have been a doctor. Both my parents were doctors. But they had decent handwritings. It's only mine that's bad. But it's terrible, you know, in the pharmacy, they have to read it. They have to understand it. And what if they give the wrong medicine?
Doesn't matter. That's just a secret language of pharmacists.
Perhaps. And of course the doctors use symbols that can be understood, handwriting or no handwriting. But, okay. Next example. Limit of tangent of 3x over sine of 4x as x tends to 0. No, no x at all. We have only tangent and sine. There's no x. What should we do? If there's no x, we put it there. So for this, we would like to have 3x in the bottom, on the bottom, because tangent t to t, the limit would be 1. So if I have tangent of 3x, I would really like to have 3x there, because then this limit would be 0. Of course, because I made 3x, I put 3x down there, I have to put 3x up. 3x up. Alright, now, for sine, I would really like to have 4x where? Up. So the only correction I need to make is 4. I don't need another x, I already have an extra x there. So I multiply by 4, and now what I have there is this limit. You can see this limit is also 1. If sine t over t tends to 1, then obviously t over sine t also tends to 1. It doesn't matter that it's upside down. It's still the same 1. It's 1. If the limit value was something different, like 5, then of course this would be 1/5. But in this case, if it's 1, we can turn it upside down without any bad consequences. And for the tangent, we have this limit, which is 1. So this tends to 1, and this tends to 1. So what's left over?
4.
3 over 4. So if there is no x, we can simply put it there somehow. We can multiply by things if we divide by the same things at the same time. Then nothing changes. So the same would apply for if we had a combination of sine of one angle and sine of another angle, or tangent and arctangent, or arcsine and sine. If we need an extra x, well, a multiple of x, of course, 3x or 5x or something else, We just multiply by it, divide by it, and have a look at what happens. Sometimes, of course, we get an extra x, which means that part tends to 0, and we might have a 0 or infinity in the end if there are too many x's in the, if we happen to get too many x's. It might happen. It might happen. It is possible. But on the other hand, at least we have a method for dealing with this. Oh, another example. Another one. Lim when x tends to 0 of sine squared of 4x divided by 6x squared. So obviously it would be nice if we could have sine squared of t over t squared, because that means sine t over t squared, like this. So what we try to do is, probably we should try to get something like this. We should try to get something like this. So if I have sine square of 4x, what I would like to have is 4x squared, including the 4. I don't have anything including the 4. So what do I need really? So this is a matter of like playing a game, I would say. This is sine 4x squared. So I need 4x there. If I open this square, I have 16x squared. I have 6. So what happens here is I don't need 16, I need 6. So this 16 is sort of unnecessary, so I have to multiply by it, and I have to divide by 6. Because 6 is there, and 16 is not there, but I put it here because it becomes 16. I put it there, so I have to eliminate it again. So 1 squared. And the final answer will be 8 over 3 after simplifying this. So when you see sine square, you have to be very careful, because that means, so perhaps intuitively, if you look at the first example, if you look at this example, you see those numbers here, and you see the final answer. You can easily guess the final answer, right? If you look at this, if you look at example 1. 3 over 5. The example as it was written and the final answer, the numbers are there. But if you do it for this, you have to be very, very careful, because it will not be 4 over 6. Because it's sine squared. And so you have to be very, very careful. You have to be very, very careful with these situations. If they are plain things, plain quotients, then it's easy. If there are squares or other higher powers, then it becomes a bit more complicated. It's not difficult, but you have to be careful. That's the thing. Example 5. Why so many examples? Because I'm showing you the most important situations that might arise. The most critical parts, the things that you really have to know and pay attention to. So number 5. I cannot promise that exactly these very same examples are on the paper that I will email you, because I don't remember, I don't have it with me. I'm just doing it. But anyway, these basic situations are very important. So let's suppose we have lim, sometimes this happens, as x tends to 0, let's say 10x squared divided by 1 minus cosine of 3x. Evil. Right? No sine at all. Cosine. But it's still 0 divided by 0. So it's still an uncertainty. Any suggestions? What we might do here? simple trigonometry. As simple as possible. We don't want to do anything really complicated.
Multiple signs.
To convert it to sine.
How do we convert it to sine?
Multiply by 1 plus cosine
Yes.
for x.
Let's multiply by the trigonometric conjugate. Yes. 1 minus cosine 1 plus cosine 3. Well, I should have written this in another color so that I'm always trying to write the extra things, the additional things in another color so that you see which are the ones that I actually add for myself. And of course I have to multiply and divide by it, both in the denominator and the numerator. Now, move on. As x tends to 0, now we have 10x squared, 1 plus cosine 3x, divided by 1 minus cosine squared of 3x. Why is this better than this? It's still 1 minus 1. Because this is sine squared of 3x. This is sine squared of 3x. Just as I said, simple trigonometry is what helps best. So this is sine squared 3x. This is basic trigonometry. Only the basic identities. We are not using anything complicated. 10x squared 1 plus cosine 3x. Now let's analyze this one. First of all, if x tends to 0, then cosine of 0, if x approaches 0, then the cosine approaches 1. So actually this factor, yes, it tends to 2. The limit of this is 2, so it's simply a factor of 2. So at this point, I could write it's 2 lim x tends to 0, 10 x squared divided by sine 3x. Now what should I add there? I left some space.
A square.
Square, yes, thank you. So what should I add in there? I left some space.
9.
9, right. Because if it's square, we need 3x squared, which means I need 9x. So, okay, I'll write it like this. I'll write 3x squared. I need 3x squared. So this is a 9, which means I have to divide by 9 as well. Now I can see that this limit is 1 squared, upside down, but still 1. And the rest is 2 times 10 divided by 9. Okay, so it's 20 over 9. No need to change it into anything else. If you have simplified it enough, then you can leave it 20 over 9 as an improper fraction, no problem. So if I have 1 minus cosine, I can remedy this by multiplying by 1 plus cosine. Of course, multiply both the numerator and the denominator. And sometimes the difference creates sine squared. But the other factor doesn't hurt because it actually tends to 2. 1 plus cosine. If the angle tends to 0, the cosine tends to 1, and 1 plus cosine tends to 2. So this whole thing, this thing actually tends to 2. So this is again a standard method. This is a standard method. That's how it works. All right, we have 20 minutes for the second special limit. So I will email you the file, obviously. You can try solving some of these. Some of those you will find solved already. For example, this is solved already. It's actually an exercise in that paper, but I have shown it to you. So the second special limit.
1 plus 1 over x.
Yeah, right.
The power of x.
This limit is how we get the magical number e. So the second special limit. This is the uncertainty 1 to the power infinity. Why should 1 to the power infinity be an uncertainty? 1, you multiply it by itself as many times as you like, you will still get 1. So the thing is that we are not dealing with the constant 1. We are dealing with something that tends to 1. That tends to the value of 1. And it will be 1 plus 1 over x to the power x as x tends to infinity. So yes, the expression in the brackets, the base, actually tends to 1. And the exponent tends to infinity. So because this is not a constant, it's always slightly greater than 1 or slightly less if x is negative. It's slightly greater than 1. It means that when you multiply it by itself, you get more than 1, you don't get exactly 1. And even if x value is very, very, very large, and this expression is very, very, very close to 1, you still multiply to a very large power, which means it still creates some mass, if you like. So if we check this, you can do it at home with your computer, for example, in Excel you can create a table and simply go on and on and on for the x values, choose a step. You will see that after a while you will notice that the values go closer and closer together, so we are getting a limit. As x tends to infinity, this value approaches something. This something is the magical number e, which is 2.71 something. If you have a calculator, you can look it up. So this is we might say it's a magical number. Funny enough, it's one of the basic constants in mathematics. Nobody has invented it. It's discovered because if we create this kind of sequence, we discover this constant e, which is the limit of that sequence. It's somehow built into our mathematics, into our universe, into our reality. Mathematically, it's a very abstract thing. Nobody invented it, nobody created it. It just is, just like pi just is. So this is one of the basic constants, and this means that mathematically we are somewhere very, very deep, really deep down, close to the roots somehow. So how do we use this? How do we use this? Normally we get examples. Normally we get limits like 1 plus 2 over 3x to the power 5x minus 1, something like this. When x tends to infinity. So again, if we have this, there's no problem. We simply write e as an answer, and that's all. No problem whatsoever. In this situation now we have a problem because this is not exactly these two numbers are reciprocals, 1 over x and x. These are not exactly reciprocal, so it's not really that. This is where we force things a little bit. Mathematicians have this nasty habit. If we don't see things fitting, well, a certain frame, we just squeeze them into a box. We push them into a box. We give them the shape that we want. We give them the shape that we want. We are a little bit forceful. So I'm going to force it to become that somehow. Let's see. I am introducing a new variable. Let's call it t. I'm introducing a new variable such that 2 over 3x, let's rename it. We want 1 over something. Okay, 1 over t. I'm simply forcefully renaming it. 2 over 3x, let's call it 1 over t. In that case, so we can, at this point, we can, of course, express x from there and put in there again. That would be, I would say, not the most efficient method. So if x tends to infinity, we see that t must also tend to infinity. So that must be, that should be written there. So now let's see what becomes of our limit. We have now 1 plus 1 over t to the power some expression. If I try to get x out of this and put it there, it's becoming unpleasant. So what I do is, what I really want is not that unpleasant expression. What I really want is t here, because I want e. So, all right, I force. I want the t there, I put t there. That's it. So you see, mathematicians are capricious. I want it, I put it there, that's it. But what else should we do now? It's the wrong exponent, it's wrong. If this, by definition, by the way we define it, this is right, this is wrong, because that's not what we have there. So, we correct our mistake. We multiply it by 1 over t, now this is 1, and then we multiply it by what we really had there. So, what we really had there was 5x minus 1. So you see, now the exponent is correct. The exponent is correct. T times 1 over t is 1, so this doesn't change anything for the whole expression. But at the same time, I did get my way. I did get this, which actually tends to e. What is 1 over t? I see it there. It's there. It's there. So there's no problem really. So this is actually, it seems that this limit is more complicated than the trigonometric limit. In reality, it's actually simpler, I think. X tends to infinity. So here I should write that t tends to infinity as well, because I'm using two variables in the same expression, so I should write both of them there under the limit. Now I'm going back to x tending to infinity. In other words, this part, this green part, tends to e to the power 5x minus 1 and 1 over t. I put this. So it's 2 times 2x, 5x minus 1 divided by 3x. In other words, I put back 2 over 3x back instead of 1 over t. And now what I really have is e to the power limit, because e is e. Now I need to find the limit of the exponent of this. X tends to infinity. 10x minus 2 over 3x. Now, what is this limit? 10/3. Remember that for this kind of limit, if you don't remember, then I'm reminding you for one last time. 10x over x minus 2 over x, 3x over x. Remember, we can divide out x. So now this becomes 10 minus 2 over infinity, which is 0, divided by 3. So it's 10 over 3. So this is e to the power 10/3, or I could write cube root of e to the 10th, using the definitions of exponents that are rational. Remember that a ratio, a rational exponent, means that the denominator becomes the index of the root of the radical, and the numerator becomes the normal exponent. So this is how this kind of limit works. Let's have a look at one more. For example, if we have subtraction instead of addition, perhaps we might have 1 minus something, not 1 plus something. Okay, this was the first example. The second one, okay, I'll write it here. Okay. X tends to infinity, 1 minus 5 over 6x to the power, let's say, 12x minus or plus 3, something like this. Okay. So now I do the same thing. It doesn't matter that it's negative. I can call a negative expression minus 5 over 6x. I can rename this 1 over t. No problem. I don't like the minus. I include it in the 1 over t. As I said, mathematicians are quite willful people.
Silly.
No, not silly. Willful. I want this. I'll make this. I don't care what else happens. So what we have now is 1 plus 1 over t, because I included this minus sign in the 1 over t. I included this minus, so that's why I have a plus here. Now, of course, I want t, I want 1 over t, and I want the original exponent 12x plus 3 as t tends to infinity and x also tends to infinity. Okay, this part will be e. This part will be e. So I have lim of e to the power minus 5 over 6x times 12x plus 3 as x tends to infinity. Now I need to find the limit of this. I can do it somewhere on the side, so the limit of minus 60x minus 15 divided by 6x when x tends to infinity. This limit, again the same, divide out x.
Yeah.
So, no, it's not 1.
Minus 10.
It's minus 10. So I have e to the power minus 10, which means 1 over e to the power 10. So it actually takes one line of writing. It doesn't take too much to deal with this. Of course, sometimes this exponent might look slightly different, slightly more complicated. For instance, I might have not x or 3x, I could have something like 7x minus 10. Instead of just a constant times x, I could have something else. I could have something like 10x plus 2, 2x minus 7. So the thing is, whatever happens, whenever we have a suspicion that this might be the e limit, we replace the unpleasant part by 1 over t, and then the rest is simply mechanically. You have to remember what to do. You put t because we want it to make e, but then we have to put 1 over t to balance that, discard, delete that one, and then we put the actual exponent there.
Can we don't use the t, just write the answer like this?
Ooh, write the answer. How do you write the answer? Like this?
Yeah.
Huh.
Because you just illuminate everything.
Okay. All right. Some people might. I'll know who can and who cannot.
And to prove that?
No.
Like
No. I simply know that some people will be able to do this very quickly, and that's actually another hint that we might do. So, well, actually, usually when I see this kind of limit, I can write the answer immediately, at once. But, well, I would like to have something in the middle, not just question, answer, something, not much, but something in the middle, something that you need to write. All right, and the last probably one, extent, or perhaps, no, I'll squeeze in 2 examples. I'll try to squeeze in 2 more. Extends to infinity. Let's take this one. 2x minus 6 divided divided by 2x plus 3 to the power x minus 1. Okay. Does this look bad?
We can partially divide.
Yeah, we can simplify. We can see that if we divide these two expressions, we'll get 1 and then something, a quotient, exactly. Or we could manipulate, of course, we could manipulate a little bit. 2x plus 3, I could do 2x plus 3 minus 6. Because this way I can see that I can divide out 1. So this will be 1 minus 9 over 2x plus 3. So some extra manipulation. Like this. So I have 2x minus 6 over 2x plus 3. I manipulate this expression, this quotient a little bit so that I can separate the 1. For that, obviously, you have to notice that coefficients of x have to be the same. Because if they are not the same, then the quotient will not be 1 when you divide these. No. If you divide, for example, 3x plus 1 over 2x minus 1, it will be 1.5 plus whatever fraction. So the thing is, if we have 1.5 plus something that tends to 0 and to an infinite power, it will be infinity. As soon as these are not the same, as soon as we have different coefficients, we do not have the e limit at all. We have either infinity or 0. So you can try to check. And then of course I'll say, alright, so 1 over t will be minus 9 over 2x plus 3. And obviously, if x tends to infinity, then t tends to infinity. So I can rewrite this as 1 plus 1 over t times t times 1 over t times x minus 1 if t tends to infinity and x also tends to infinity. So if I do all these extra things, first of all, it's best to keep them together. That's why we are using these sort of square brackets. They are not really brackets, but we are trying to keep all those extra transformations in one spot so that we can actually check things. So I don't need to write too long, too much. Now I have, of course, this. So it's lim of e when x tends to infinity of 1 over t is now this. So it's minus 9 over 2x plus 3 times x minus 1. Now this limit, again, somewhere, is minus 4.5. So this is e to the power minus 9 halves, or I can write it's 1 over the square root of e to the 9th power. Negative exponent means we have to move it down to the denominator. Exponent half, which is in terms of halves, means we have to do the square root, and 9 is the only one that's really what matters. Remember that the square root of a can be written as a to the power 1/2. Actually, a to the power m over n means nth root of a to the power m. This definition is again something you should remember from school. And we are using it here. We are using it here to express the answer correctly. Alright, I guess I can't let you go. It's time.
Okay.